Okie dokie. So we are going to continue talking about caching today. In fact, by the end of the lecture, we're going to start getting into a really interesting topic involving caching. But we were talking before about these various program behaviors. How does the program access memory? What kind of memory access behaviors does it have? And so we had these concepts of locality and stride, where basically spatial locality is that I'm accessing stuff that's near what I've already accessed. And temporal locality is that I am accessing the same thing multiple times. Which, by the way, you'll have an opportunity to practice this on assignment 5, but when we get into assignment 5 and on the final exam and you're thinking about caching, I am looking for you to be using these terms. So I do want you to understand what they mean. So there are two kinds of locality. Make sure you use the terms correctly and so forth. So it's very valuable to understand that there is a distinction between them. And then, of course, we have this stride K reference pattern, which just means I go K steps forward each time when I access things. So stride 1 is really nice. Stride 0 is temporal locality. And then obviously stride something larger than 1 is going to be less efficient when it comes to working with the caches. And so we looked at the basic cache designs. Let me see, yeah. So we had this notion of cache sets. Every block maps to a specific cache set. It's hard-coded into the hardware, so it's not able to be changed. And cache sets can have anywhere from one to many different cache lines, in which case we have various trade-offs in how we design our caches. And so just quickly to go over these, I don't want to spend too much time because you have last lecture to look at, but we had direct map caches where there was as many sets as there are lines. So every cache set has exactly one cache line. It's super simple to design because basically when you get an access come in, you map it directly to the cache set that it belongs to using the set index. You can see where that's taken from the address that comes in. And you take the remaining part of the address, and that's the tag, and you just compare the tag in the cache line with the tag of the address that's being accessed. And if they're the same, then you have a hit. And if not, you have a miss. And if you need to evict something, again, it's super simple. I only have one choice, so I just evict that line, and then the next line goes in there. So that's direct map caches. They're super simple. This was our simple example here. 4 lines, 4 sets, everything is simple. Fully associative caches are sort of the other end of the spectrum. We have one set, and all the lines go in the set, so we don't have any set index for that. But we do have a very large tag now, so the tag is going to be even larger than it was before, and we have to look at all of the cache lines to see if that tag appears for any of them. Now, it'll only appear for one. If it appears for more than one, our cache has a design flaw in it, so we expect that that's going to appear for 0 lines or 1 line. But that's the big complexity that we have in here, that we have to actually do the comparison. We have to figure out who we want to evict. It gets a lot more complicated to do this. Set associative caches blend these things. So now we have some number of sets and some number of lines per set. And the logic, you have this trade-off. It's easy to identify the set, so that allows you to narrow down where to look. You have a small number of lines to look at. And you'll notice today that when we look at the way that like the Core i7 series processors work, it's like 16 lines per cache set or 8 lines per cache set. So there's not very many, so the logic is a lot simpler. And of course, we've only been talking about reading, but there's also writing. Programs have this unfortunate reality that they also write to memory. And so we have to figure out how to incorporate that into our caches as well. And if there's locality of writes, then we would like to have our cache give us some benefit so that we can leverage that locality of writes. If I'm loading a whole block and I have a whole bunch of writes to that block, I'd like to sort of cache up those writes and then perform them all in one shot. So if we have a situation where the program writes to some address and that address is in the cache, then we call that a write hit. And we do have a couple of different choices. Thankfully, we usually choose the good options because we have lots of transistors that we can cram on systems now, so we can build these complicated things. But we have the simple option, which is slow, which is write through. So when I write to a particular block, I always turn around and write that to the source of the block as well. So you see that I don't get any benefit from performing my writes in that situation. Every write is going to incur that full memory access cost. I'm not just going to get the cost of writing to the cache. So that's write through, and it's not very appealing. So mostly what we use nowadays is write back. And write back means that we have to keep a little bit of extra bookkeeping with each cache line. You can see that we add a new flag to each cache line saying, is this cache line dirty? Does it contain any data that's been modified and not reflected in the source of the data? And so when somebody performs a write, we just perform the write against the cache line, set the dirty flag, and then later when that cache line is evicted, then we turn around and write that block back to main memory. So you can see already that it's starting to get a little bit more complicated, because when do we evict a line? Well, typically it's because some other read or some other write was occurring. And so we have to perform a read from the next level of the memory hierarchy. We have to read that into the cache. But before we can do that, we have to write this back. So we have a write and then a read occurring. And so you can see that caching definitely increases the complexity of the memory interaction, but it is so worth the performance gain that you get from it. So write back, we can now exploit locality of writes as well as locality of reads. And if I have a situation, remember our little vector add program, where it was reading AI, BI, it was iterating through the vectors, and then it was writing to RI. Well, we can cache those up now. And we can perform all of those writes back to main memory in one write, as opposed to having to perform a whole bunch of smaller writes and incur that cost over and over again. So we get a big benefit there. And of course, like I say here, it is more complicated than write through. We have to sort of arrange these reads and writes. We have to make sure that we perform them properly. We have a slight bit more bookkeeping, but it's really not. The bookkeeping is not the real cost. The cost is figuring out the whole interaction with memory. Okay, so that's writing to caches. Any questions? It's pretty straightforward. Now we can have another situation that's even more unusual, which is that I want to write to something and I haven't read it yet. That was in fact what we had with our AI plus BI becomes RI, or gets stored into RI. When we had that situation, we could have a situation where we want to write to a block, but it's not yet cached. And so that's an even more unusual situation. We call it a write miss. And so we have several different ways that we can handle that as well. If it's not in the cache, we could just go ahead and load the block into the cache and then perform the write against the cache. Okay? Because again, we're assuming that there will be subsequent writes. It's generally a good assumption. So that's write allocate. That's the more complicated one. No write allocate is the simpler one. If I have a write miss and it's not in the cache, I don't load it into the cache. I just go ahead and perform the write against the next level of the memory hierarchy. So again, you can see that option 2 is going to be slower, but simpler to implement. Option 1 is more complicated, but it's definitely going to give us more benefit. So write back, remember write back means that we are caching up writes in the cache, so we don't just write straight through to the next level of the hierarchy. So write back is typically going to use write allocate. Write through, where we perform every write to the next level of the hierarchy, just to keep things simple. That typically will also use no write allocate. So if you're gonna make one of these simplifying choices, then you typically make the other one as well. If you're gonna make it complicated, you might as well do all the parts of it and get the full benefit of it. Okay, so those are some terms that come from writes when it comes to caching. Now, one thing that you notice, and I used to do this a lot, and I've kind of steered away from it because it is really incredibly complicated. We talk about caching in terms of, I have one cache sitting between the processor and memory. And that's kind of a pipe dream. We have more and more layers of caching now. We have now 3 layers of SRAM caches between the processor and main memory. If you have like an i-series, a Core i7 or something like that kind of processor. So basically, what you have to do when you're talking about cache performance is that you measure it. You can't really simulate it very well. I mean, I should be careful with that because anybody here like Valgrind? Anybody here use Valgrind very much? You should. It's totally awesome. If you don't, do it. Just do it. But there's another part of Valgrind that's built into it called Cache Grind. And Cache Grind simulates the cache behaviors of a program as it executes. So it can tell you what's the miss rate, what's the hit rate at various levels of the cache, and you can configure it differently and see how things behave. So that's nice. You can simulate it, but Valgrind is a very sophisticated simulation of how a processor works. The other easy thing to do, though, is to just measure the actual processor performance. There are just a few parameters that you can use to sort of experiment with this conceptually, but honestly, it's not a very good way of estimating. There's all kinds of little nuances that I'll try to point out a few of them as we go along. But we have the miss rate. That's the fraction of memory references that result in cache misses. Again, that would be for a particular level of the cache hierarchy. So miss rate is number of misses over number of references, so you can see it'll be between 0 and 1. The miss rate is almost always never 0 because we have things like compulsory misses and so forth where we can't avoid it. The cache has to warm up. And then the hit rate is just 1 minus the miss rate. Okay, super simple. Now, even when we have a hit on the cache, we still have a little bit of a cost associated with it. Ideally, that cost is going to be much less than the cost of a miss, but we have to do things like figure out what cache set. Well, that's pretty easy, but it's logic. It takes time. We have to figure out what line contains our value that we're looking at. So we have to look at the blocks tag and do the comparison and everything. And then we need to figure out the offset within the block and retrieve that value. So all of that takes a little bit of time. It's much worse, of course, if we don't have a hit. And so this is the miss penalty. And notice we try to lump everything in, but there's a lot of things we may actually not be capturing in this one number. It really kind of can't be one number. So cache set identification, checking tags, blah, blah, blah. We realize, oh, it's not in there. And now we say, okay, well, I need to load a new line from the next level of the hierarchy, but I may also need to evict a line. And if that line is clean, I just say, forget about the old data, and I load the new data into that line. If the data was dirty, then I have to now write that back to the cache. Okay? So you can see that we're kind of assuming a lot by trying to attach a single number to all of these things that may happen when we have a cache miss. But hey, it's an approximation, and so that's what we'll use. So let's say that we have a hit time of 1 clock and a miss penalty of 100 clocks. Typically, you do not want a computer system that's designed this way. It's much more smoothly staged, where it might be a hit time is 4 clocks and the miss penalty is 25 clocks. And so the hit time on the next level might be 25 clocks and the miss penalty is like 75 clocks or something like that. So they try to stage it much better than this. This is just to really illustrate starkly how you get a benefit from caching. So if all my reads were from cache, reads would be 1 clock. If all my reads were from main memory, then every read would be 100 clocks. And so you can see I could have a 2 order of magnitude performance improvement by using my cache all the time as opposed to using main memory. So let's say we have a hit rate of 80%. Okay, this math is really simple. I bet all of you could figure out exactly how to do this. Okay. So we'd have 80% times 1 clock and 20% times 100 clocks. And we'd end up with, on average, 20 to 21 clocks per memory access, which is way better than main memory. But one of the things that's kind of surprising is that even an 80% hit rate is kind of really bad. And you notice that in a lot of people who design cache-friendly algorithms, 80% hit rate is like, oh, I'm doing terrible. I want to get much, much, much better than that. Because you see the performance improvement really start to show up quickly. So hit rate of 90%, same math. Now we're down to about 11 clocks per access. Now if I go to 99 or 95% hit rate, then I'm getting around 6 clocks. So you can see that as you improve the hit rate, you get a very dramatic performance improvement in your programs. Okay? And if you have something where you're getting up to like 97, 98% hit rate, which is where you really want to be, then you are going to get your large memory for almost the cost of the small memory. It's not going to be quite as good as just the price of the small memory, but it's going to be pretty dang close, and you're going to have really good performance. Okay? Any questions? One of the really impactful things that I came across when I was in high school and then later on when I started learning about computer science and learning about programming was an article in a programming magazine where this guy was talking about writing a video codec. You know, I want to watch pictures of kittens being cute on YouTube or whatever. And so he was writing a codec, and this was obviously before the internet was really widely used for this kind of thing. But his codec originally had 4 passes in it, and what he did was he made 4 passes over the entire frame. So 1 pass over the entire frame, another pass over the entire frame. And what he found is that his codec was not able to meet the performance requirements so that he could get fast playback. And so what he did was he broke each frame into chunks, and he did all 4 passes on a little chunk, and then he did all 4 passes on the next little chunk, and all 4 passes on the next little chunk, and so forth. And suddenly his cache utilization was much, much, much better than it was originally. His hit rate went up to the mid to high 90% for his system. And suddenly his codec was awesome as far as performance was concerned. So it's one of those weird things because caching is one of those few circumstances where adding more loops to your program makes it faster. Because now instead of just doing a few loops, now you add more loops so that you can break things into little chunks, and you try to use the cache size as a guide to how large the chunk should be, and you get a much, much higher performing program. Okay, so that's one of those things that you start to notice. The old assignment 5 problem where it was a matrix transpose, that was how you solve that problem. Add more loops, you break it into chunks. The new problem is a little bit more interesting. It doesn't really quite go exactly into that area where it's so obvious you just break it into chunks, but you'll get to use your brains, you'll get to think about how to solve that problem. So it should be fun. Okay, the higher the hit rate, the better. That's really all you need to take away from this. And 80% is definitely not good enough. Now, when you're designing a program, obviously you'd like it to take advantage of the cache as much as possible. And obviously compilers that know how to lay things out appropriately. There's this whole special art of arranging data structures in memory so that you can make them fit into cache lines as best as possible. So that's one of those things that people really, they don't really realize anymore because we write stuff in Python, we write stuff in Java, and we're like, caching? What is caching? You might see it with the disk, but you don't really see it in the hardware with memory. The cache designers also have interesting challenges to deal with because obviously they want to maximize hit rate. They don't want to increase hit time. How can I maximize hit rate? Well, if I make the cache larger, obviously I'm going to increase the hit rate because now I can have more data in my cache. But I grew the memory, so physics starts affecting the performance of that. Okay? So, I have larger block sizes to address into. I might have more cache sets or more cache lines. I have more logic to consider all of those things. So you can see that as you increase these various dimensions, you kind of run into physical limitations that we talked about before. I make the block size larger. Well, I still have to address into it. And not only that, but I have to transfer that back and forth, so that starts increasing the time there. I can try adding more cache sets. Well, now the cache set addressing logic gets more complicated. I can try adding more lines per set. Well, now my line identification logic gets more complicated. So all of these things, it's like you tweak little knobs and you try to get it to the performance that you find acceptable, but then you can't really, there's no free lunch, particularly at this level. Okay, what about increasing the number of lines per set? So then this is obviously for associative caches, not for direct map caches where we don't have this problem. Because if I want to increase the number of lines, I just increase the number of sets. But if I have associative caches, this is what I was saying before. The complexity of the line matching goes up. My eviction policy or my line replacement policy now gets more complicated because I have more things to choose from. So all of these things have an effect when you're designing caches. So cache design is pretty challenging, and I think that generally what people do, this is not an area that I have personally been involved in, but I imagine what processor designers probably do is they come up with a design that fits within the constraints that they find acceptable. Like I said, L1 might be 3 or 4 clocks away. L2 might be 25 clocks away, and they're comfortable with that. So they design a cache that can be accessed in a maximum of that many clocks. And they just make it as large as they can for that number of clocks. Okay, here's a few details. So now we're going to start talking about some implementation details, it starts to get pretty fun. I'm going to show you some interesting pictures. The processor, Intel processors have 2 different caches for instruction and data. Remember, I mentioned this when we were talking about Harvard architecture versus von Neumann architecture, where inside the processor, we actually kind of do follow a Harvard architecture where the caches are separate so that the instructions can be processed by one part of the chip and the data can be accessed by another part of the chip. It's kind of easier if we keep them separate. So we call them I caches and D caches. If you use cache grind, then you'll notice that that's what we call them. And if you read any literature about any processor with multiple caches, it'll probably use these terms as well. I cache versus D cache. Okay, so Intel Core 2 processors. I don't know, is anybody still using a Core 2? Do you know? Anybody not know? It's okay if you don't know, because I have a program in Assignment 5 that'll tell you. But okay, is everybody using like an i-series, i5, i7? That's what I would expect. Okay, so I'll probably take this slide out next year. But you can see here, Core 2 is going to have like 8-way set associative caches for just about everything on the processor itself. And the block size all the way through is 64 bytes. That's one thing that you generally notice is that all these processors have a 64-byte transfer size or block size. And we have 64 cache sets at that level, and so if you do the math, 8 times 64 times 64, you end up with 32K. And I believe that i7 has kept that, or the i-series processors have kept that 32K instruction and data cache size. And then the L2 cache is where they make it really giant, where they're actually moving data into the processor itself, but not necessarily into L1. And so you have a huge number of cache sets that's scaled, still 8-way set associative, and still 64-byte blocks. Okay. And what you notice, you'll see an experiment on this when you look at Assignment 5, but these are not that we don't have that many lines per set. It turns out that you don't have to go fully associative to have a useful cache for the way most programs work. 4 cache lines per set, 8 cache lines, 16 lines per set is actually really good for approximating fully associative cache behavior, and it's way cheaper than building an actual fully associative cache. So that's why the associativity on these is pretty low. It's because you can get pretty close to what you need to do without a really high associativity on these caches. That's one of the really interesting things about this. I just find that really fascinating, that you can get, just because of the way that most programs are written, you can get there pretty well by having a low associativity. Okay, so here's the i7 cache, just so you can see. This is what I have in my laptop. And probably many of you have i5s or i7s that you have access to. So you see again that the L1 caches are still 32K. So 8-way set associative, 64-byte blocks, and 64 cache sets. And then L2 is a little bit smaller because we want to sort of smooth out the jump between these different caches. So L2 cache is going to be a little bit larger, so that's going to be 1/4 of a megabyte. And then L3 is where we start making it really beefy. So L2 is going to be a lot faster to access than L3, but it's still slower to access than L1. And you'll notice here each core has its own L2, and then all cores share an L3. Okay, so any questions about these numbers? We have a sense about how we might intuitively expect this to work, but it turns out that you can actually measure it as well. What we do is we build a program that accesses memory with a particular stride. That's one knob that we can change. And then we can have another knob, which is how much total memory are we accessing? And we can just access it over and over again. So that's another knob. So allocate an array of size elements to scan through. And then we have that K, we just turn that K up. We start from stride 1, then we try stride 2, stride 3, all the way up to some large value, where large is like 64. I mean, at some point, if you are measuring cache lines that are 64 bytes, why would I start doing stride much, much larger than that? I mean, it's like there's not really a point in going much larger because you'll just see it tapering off. And so we'll scan through this memory for each stride value, and we repeat this process. Why do we repeat it? Well, so that we can see temporal locality as well. And as the memory gets larger, it won't fit in one cache. So we'll have to fall back onto the next cache. And so we keep accessing stuff, and when it doesn't fit in that cache anymore, then we can go to the next cache. And so we can measure the performance of these various things. Okay, and this is where it's important to keep in mind these two kinds of locality. Spatial locality, I access stuff close to each other. As the stride goes up, spatial locality will go down. And temporal locality, where I access the same thing multiple times. As the size goes up, temporal locality will go down. Okay, when our working set and stride are small, what do we expect to happen? Which cache should that end up being in? Really simple, right? We'd expect it to be in L1. Let's say that our working set is like less than 32K. Hey, it should all fit in L1. Our stride will be small. What performance should we see? We should see our L1 cache performance at that point. What if the working set gets too large for L1? Well, now we should start seeing L2 cache performance size. Because as we're accessing things, it's getting loaded into L1, but then we access more stuff, and those lines that were in L1 get pushed out again because we have to load other things. So we should see the cache that they all fit in. So we should see this tapering, especially as stride is increased. Okay, so I'll show you some pictures pretty quick. Yeah, so when all of our accesses miss L1, then we start seeing the L2 cache performance. Okay, and so forth. So we should get this smooth degradation of performance. And we can plot these numbers. This is the Core i7 Memory Mountain. I don't remember what system I ran this on. I think it was a friend's system that he got for his research. So you can see how you have multiple levels of sort of plateaus in this memory mountain where you see the various caches sort of hitting. Okay? So Core i7, 2.67 gigahertz, 32K L1 data cache, 256K L2 cache, 8 meg L3 cache. So there's this really cool instruction. I don't know if any of you have trolled through the IA32 manuals. I kind of hope not. I haven't even done that. But there's a really interesting instruction called CPU ID. I think it's called CPU ID. And that will actually give you all kinds of details about the process. You can actually ask the processor what stuff it supports. And it can say, oh yeah, here's my caches. Here's my instruction set that I support, and so forth. And so you can actually ask the processor to tell you what are the caches on the system. And so you can actually retrieve all this information and see if the information it tells you lines up with your measurements. And generally, it completely does. It's really cool. Okay, let's see. So we have a few discussion points about these. So as I increase the size, you'll notice the size is the dimension on the right coming out. So 2K, 16K, 128K, and megabyte. We have to go all the way up to 64 megabytes because these caches are getting larger and larger. You wouldn't do this on an AT processor, although you probably wouldn't run this at all on an AT processor. So as the working set gets larger and larger, like I said, you start accessing lines and they get loaded into L1, but then the next access may push that line out or subsequent accesses before you get around to using that again. So you see this drop off in memory performance because the working set stops fitting in the various caches. So when the working set is really small, you have this really fast performance, and that's the L1 cache performance. And then it tapers off to L2 cache performance. And then when it doesn't fit in L2, you start seeing L3. And remember, L3 is really large, L2 is small, and L1 is tiny. So these plateaus get wider and wider as you get down to main memory. Okay. Also, we have stride. We increase stride. That's left or right. That's the S1, S3, S5, S7 across the bottom. Those are the stride numbers. And obviously, if I'm doing stride 1, then I have a whole bunch of accesses into that same cache line. Well, when I double the stride, I have the number of accesses to that cache line, because I'm doing every other one now. Okay. And then I get to the next one, and the next line, and so forth, and that cache line has to get evicted at some point. And then it gets loaded. So we would expect that as the stride increases, our cache becomes less effectual. And so that's why we see this slope from the left to the right, because cache lines get used less and less frequently as we increase the stride. Okay? Yeah. Where are you talking about? Like on the right side of the mountain? Top right. We will talk about that in a second. There are some measurement anomalies that occur in these things. Yeah, it's really weird that it looks like the mountain has a peak and it goes down on the other side. The way that this program is constructed is it actually uses function calls to scan the memory. And at some point, the function call overhead starts to overwhelm the measurements themselves. And so that's the issue that we're seeing. Because you can imagine if I have a small working set to traverse and I have a large stride, I get through it really fast. So I start, end, and then the function call overhead starts overwhelming that measurement. It becomes too imprecise. So you do have some of those things going on. There's a few other anomalies that I'll point out here as well as we go through this. Now here was my old laptop, which happened to be a Core 2 Duo. That's what I had at the start of the term. One of the things you'll notice is that the performance, the maximum performance, is much worse. I had maybe 850 megabit or megabyte throughput on my memory bus. Not very good. I'm sure this system is much better. I mean, it's like the old one was 2009, so that's like 6 years ago. But you can see that Core 2 only had 2 levels of caching. And you can see how severe a drop-off it is as each level of cache becomes ineffectual. So that's why we don't like this. And as the processor performance gets better, we want to smooth this out so that program behavior, program performance degrades more gracefully. Okay, so you can see here 32K L1 data cache, 3 megabyte unified L2 cache, so it had 2 cores, as you can see, Core 2 Duo. And so the L2 cache size was larger, and so we get a wider plateau there. Okay. Yeah.
So in the previous graph, we noted that as we moved towards smaller size and basically that side of the graph, it was getting higher. Mm-hmm. In this case, we have a plateau that's off on the left that then dips back down as side drops off.
Yes. Yeah, so that's basically, I believe, if you're talking about the other side of the mountain that we can't see.
Yeah, like there's a green section that goes back down into brown.
Yeah, and so that's where I believe that what we're seeing is artifacts from function call overhead that are interfering with the measurements themselves. Because I tried running the same program on this system, and it's even more extreme what happens. Because as the memory access cost gets so small compared to the function call overhead, you really start seeing, like, the mountain has this weird, there's basically, you'd have to throw away all those measurements because they're not very useful. That's really, the margin of error on them is much too large. That's why, yeah, you see it dip way down, and it just doesn't make any sense, except to explain it by the overhead of the measuring process itself. Typically, just as an aside, and you'll notice this on the 5th assignment, when you have small, fast things that you need to measure, how do you do it? Well, you certainly don't do it once and like try to start and stop the stopwatch. That's dumb. What you have to do is do it like 1 billion times. And then start the stopwatch at the beginning, do it 1 billion times, and then stop the stopwatch at the end. And then just divide your answer by 1 billion. And now you have a pretty good measurement. Okay? So this is not anything new. I'm not telling you anything magical. But when you're constructing systems, software systems, and you need to measure the performance of something that's really fast, you have to consider all of these little details and nuances. And I have a feeling that, like, I didn't write this program. This is a program that comes with the textbook. And I have a feeling that it has this limitation, that it wasn't constructed quite right to give us really good measurements all the way back to the back. So that might be something that would be interesting to explore in trying to make this program a little bit more intelligent so that we can get good measurements all the way back to like 1K memory sizes and so forth. Maybe if I have tons of time and I'm bored, then I'll work on that. Would people like to try this program themselves? Anybody? I'll throw it up on Moodle, and you can give it a run if you see anything obvious. The other thing that's fun and also really infuriating is that there's a couple of instructions we use for this called read timestamp counter. And what it is it basically allows you to measure the number of processor clocks that have elapsed. This instruction is awesome, or at least it was until 3 to 5 years ago when processors got so good that they start turning parts of themselves off when they're not needed. And then that read timestamp counter thing became nearly useless. And so the old version of the textbook actually had a section about measuring program performance. And then processors got too good, and they just tore that section out because they're like, all this measurement stuff is not very useful anymore. And I include it in some of my programs because it does give you a rough gauge as to how good things are. But it's pretty bad now because, I mean, if you have a processor just turn itself off and then come back on, it's like, what is that timestamp counter telling you anymore? There's all kinds of other ways in which it can be affected now. So, I mean, it's just like, oh, it's terrible. Measuring program performance is very challenging. And so on assignment 5, I just kind of phoned it in, and I'm like, we'll just use wall clock time. It's kind of the best that I have, which the nice thing about timestamp counters is that you can actually use them even if you have other things going. You're playing your cat videos at the same time or listening to music or finding Mersenne primes or whatever the kind of stuff is that you like to do, computing rainbow tables. Then, like, even with that, the timestamp counter will be correct and accurate. But wall clock time will vary widely. And so it's like now that the timestamp counters are becoming less useful, it's frustrating. We can't really get an accurate measurement of how many clocks a particular computation takes. So it's one of those things. It's just an unfortunate reality that we have. Okay, now Core 2 has 2 caches, so you see I already talked about the degradation there. This is where, like I said, I suspect that the way that the program has been constructed is giving us poor measurements when we get to a certain size, where the memory access cost is so small compared to the other costs involved in the measurement program, that we see this horrible dip, which doesn't make any sense because you have tiny, tiny memory access. That would be outliers that you would generally toss out if you were trying to actually sort of model the performance of the system. You would toss out those outliers. Now, you also notice this other really weird thing that around, I think it's stride 16. Yeah, it's right before stride 16. You get this weird little bump in the performance as well. And what I believe this is as you're accessing various cache lines, you'll have a few hits in each cache line, and then you'll go to the next cache line. At some point, that cache line needs to be evicted. But you've got a set associative cache, and so the system can keep some of those cache lines around. And so it may be that as we get out and then we come back to some other access, that cache line is still there. And so you see a little bump in the performance just because the stride has gotten just right to allow you to access that cache line again. So there's some really weird behaviors that you can notice in cache performance. So our stupid little, here's the hit rate, here's the miss penalty, here's our computation to say this is how fast things are. You can see how approximate that is when you look at real cache performance. It's so complex. And so just measuring it and trying to understand it is about the best thing you can do. And even with that, there's going to be stuff that's difficult to understand. Okay, yeah, so I talked about that. This was another Core 2 quad, just to illustrate that the motherboard has just as much of an effect on performance of memory accesses as the processor itself and the caches. Notice the peak here. It's just over 7 gigs per second, 7 gigabytes per second. Here, it's like not even a gig per second. That is as much due to the motherboard chipset as it is to the processor itself. So I wanted to point that out, that it's not just the processor. The processor is very important, but you have to take the whole picture into account. But you'll notice that everything else is very, very similar. We still got that weird little ridge on the right. We've got that weird tapering off thing in the back. Probably the plateaus are about the same size because I don't think that it looks like the unified L2 cache might be a little bit larger. Yeah, so we had a 3 megabyte unified cache, and the Core 2 Quad had a 4 megabyte unified cache. Okay, so any other questions? Ones that I'm actually capable of answering definitively? All right, so that's an idea. I'll throw up that stuff for you, and you can get a sense of how that stuff works. But you can see how important caching is in systems, and you'll see that really illustrated clearly on assignment 5. I'm really optimistic that this is going to be a good problem for you to solve. And it basically is the way that we're solving this performance gap that has emerged as everything has gotten faster, but things have gotten fast at different rates. So we can have caches that give us large memories that are close to as fast as small ones. And as programmers, it is very important that you're aware of these things so that you can write systems that are fast. I mean, I think just about everybody in here is familiar with programming in Python, right? Python dictionaries are designed to be cache-friendly and cache-efficient. They're very interesting to read about. So if you're ever bored and you want to look into something interesting, look at CPython's dictionary design, because the way that it's implemented is supposed to work well with caches because they know how widely those data types are going to be used. Okay, so very important. Now, just to transition into the next topic, which we will start talking about today, I don't know if you've noticed how processor speeds have kind of tapered off. We're around 3 gigahertz. I mean, this is probably like the third system that I've gotten in my life that's in the 2 to 3 gigahertz range in the last like decade and a half or something. It's like we've gotten up there, and then we just kind of topped out. And there's various physical issues, again, that have prevented us from getting faster. One is clock signal propagation that you'll notice. Heat dissipation, those kinds of things. And so we basically have switched our approach in how we design these processors to try to do as much with as little as possible. So we started introducing all kinds of parallelism in these systems wherever we can. Okay, I've mentioned quite a few times, pipeline instruction execution. Okay, I'm doing one instruction, but that doesn't mean I can't start loading and decoding the previous instruction. And I can't do memory accesses and ALU operations all at various phases, so that I can have multiple instructions in flight. And then we have superscalar architectures. I mean, it's crazy. I saw some statistic that said how many instructions are actually in flight at any point in time on your processor, and it is a crazy large number. It was like in the 30s or something. I can't remember. It was huge, though. And we have out-of-order instruction execution. And register renaming is a big aspect of this, where if I have moves, I can just sort of pretend that I did the move, but I keep the value in the same place, and it just has a different name now. Not making this up. And all these other things that go on. And so you have these things that systems do. And so the result is that even though we've kept in the same clock speed range, the processors are still getting faster. They can do more and more just with that clock speed. So you can see that clock speed is not really a good estimate of processor performance at all anymore. So another approach that's kind of emerged is I'll just stuff multiple processors onto the chip. Okay, and so I have all these things listed. The cell processor was used in the PlayStation. You have like 7 or 8 processors on a chip. You can use them for different things. There was somebody who was a graduate student at Caltech who I got to work with closely while I was an undergrad, who was centrally involved in the design of the cell processor, and so it was kind of cool to see that his name was attached to that. And then obviously GPUs. We have all kinds of parallelism on GPUs to do multiple pixels or multiple regions at the same time. Of course, they still have the same issue as before. The processor is still way faster than the memory. And so we still have caching in these systems. And so multi-core processors start introducing new wrinkles to the whole issue of how do we actually manage these caches. And I just want to give you an introduction. We're going to spend about a lecture and a bit talking about this topic. Okay, so let's say that we have multiple processors on our chip, and now we have caches as well, because hey, we know we need to be fast. So the question is, what new problems have we introduced by doing this? Yeah.
Well, the two caches right now are not attached to each other. So what if something's in both caches and you are, I mean, I would assume you'd end up with some sort of threading issue. If you write one of them, you not necessarily read the other.
Yes, so that's exactly right. We have an issue that these caches don't coordinate their operations at all. I could easily have a situation where, just as a simple illustration, one processor reads some data and begins doing some computation, so that block gets loaded into the CPU1's cache, and then CPU2 decides to write it. And now CPU1's cache no longer has an up-to-date value in its cache. And so if it continues doing computations based on that value, it's out of date. So we have a big problem here. So what we do is we throw some magic at the picture, and now somehow our caches are going to interact with each other directly so that we can coordinate these kinds of operations. So like I say, your CPU1 reads data in block 23, starts using it, CPU2 issues a write, and then somehow, magically, hand wave, CPU1's cache gets informed that the value has changed. And we do something about it. Maybe we just change the value in CPU1's cache. Maybe we tell CPU1's cache, get rid of that data, it's not valid anymore. Something happens, okay? So this is called cache coherence. You can have a specific mechanism that works within these caches to keep them all synchronized with each other. And we do have various constraints that we really need to follow. So like I say here, here's a few details of how we'd like our caches to behave. A processor reads a location and then writes to it. Nobody else modifies that value between the read and the write. Anything that occurs after that write should reflect the new value. We need to make sure that any subsequent access reflects that value. Here's another one. P1 writes to a location X, and then another processor reads X. P2 must read the value that P1 wrote. This kind of is exactly what the first one is again. Now, it's kind of an interesting issue here. You'll notice that we say subsequent in these things. Now, we have kind of a problem because if you have out-of-order instruction execution, what is subsequent anymore? Good luck with that one. We talk about it a little bit in the OS class because it turns out that because processors are getting so intelligent, we have to introduce a new mechanism where we can say everything that occurred before this point in my program has to be finished at this point. And anything that starts after it must start after all the stuff before it has finished. It's called a barrier. And we need to start introducing barriers if we're going to have programs with parallel execution behave correctly. Okay, enough of that. We talk about that in the OS class. So processor P1 writes a value A to location X, and then processor P2 writes B to the same location. What people or observers should see is that A was written first and then B was written, but they should never see them out of order. They should never see B and then A. These are just a few examples of the kinds of things we'd like our coherent memory to actually do correctly. So we need some kind of mechanism to coordinate these things, and the general approach that people follow is to introduce new state into cache lines. Because before we had really simple stuff. Is it dirty? Do I have unwritten writes that need to be written back to the other level of memory that I'm caching for? Okay, so we introduce some new state and new operations, and then we can do coordination between these caches. And that is a protocol, a cache coherence protocol. And there's a lot of different ones to choose from. We'll talk mainly about MSI and then variants of MSI. MSI was named by somebody who's completely boring. Probably not the same people who named garbage collection stuff. It's just named for the state names in the protocol. You have modified, shared, and invalid. So CPUs have their own caches. The caches coordinate access. And based on the state of different lines, you have different behaviors that are performed by the caches. So modified means my CPU has changed this state. So I am awesome. Everybody else sucks right now. Okay? The line contains data modified by the CPU and is thus inconsistent with main memory. Shared means my CPU has accessed this value, I have cached it, and I have not changed it. And no one else has changed it either. So everybody's sharing copies of this one cache line that nobody's changed yet. And then we have invalid, where one cache can tell some other caches, or maybe everybody else, invalidate your line because it is no longer usable because my processor just wrote to this line. Okay? So that's invalid. So like I say, if a memory block can appear in multiple caches only if it's in the shared state. If it ever turns into a modified line, then it can only be in one cache. So if my processor writes to the line, I've got to tell all the other caches to invalidate the line because I'm going to move it into modified. So a processor reads a block or reads a value from a block. If it's in my cache and it's not invalid, go ahead and read it. If the block is not in my cache, then I basically have to see if any other cache has it currently marked modified, because if it does, then I have a problem. But like I say, if no cache has it modified, then I can just read it from main memory. But if somebody else has it modified, I need to tell that cache, write it back to memory so that I can now read it. Okay? And obviously, when they write it back to main memory, they can switch to the shared state. Or they could switch to invalid. It's up to the cache to decide what it wants to do. But I have to go through this coordination now between different caches. When I write a value to a block, if the block is in my cache and it's already marked modified, that's easy. I'm already the only person with that block, so I just write the value. If it's marked shared, I invalidate everybody else with that cache line. And I now change my block status to modified, and then I perform the write. If the block isn't in my cache or is marked invalid, then again I have to look around. If anybody else has it shared, then I have to invalidate them so that I can load it and then say it's modified. Okay, so if the block is marked modified in another cache, well then I need to tell them, hey, write it back, and then either, well actually you can't switch to shared, right? Because I'm about to write to it. So you just tell them to go to invalid, and then I can go ahead and read that block and mark it modified. Okay. You see how complicated this is? How much worse can this make our program performance be? Well, we'll talk about that next time. Let me see if there's a few more things. Yeah, so what we'll do next time is we'll talk about the variants. This is the basic MSI protocol that I just described. And the variants include various optimizations, which change the names because we have new states. So it's Mezi, Mozi, Moeezy, and I'm not making that up again. But we have other interesting issues as well that can occur with cache performance on cache coherent systems. So anyway, we'll pick that up on Wednesday and finish that discussion.